The last section we have discussed loss of it due to sudden enlargement. In that, we use two equations. One is energy equation and another is momentum equation. Energy equation is nothing but Bernoulli's equation, which is P1 by rho g plus V1 squared by 2g. The Z1 equal to P2 by rho g plus V2 squared by 2g. The Z2. If there is a loss, we will add in the right side. It was earlier in the last class, loss of it due to sudden enlargement. So we added in the last right hand side of Bernoulli's equation. And then we used a momentum equation. Momentum equation is sigma x is equal to d by dt of mu. And also continuity equation is a common equation which we use in almost all the derivations, all the physical concepts. And in that way, we derived head loss due to sudden enlargement in the last section. And there is head loss due to sudden contraction also. And these two are very important for the examination point of, I repeat. See here, what is sudden contraction? Observe the figure first. Sudden contraction is nothing but when a pipe diameter suddenly contracts from bigger diameter to smaller diameter. So that is what sudden contraction. And there you see, observe, when a fluid flow is flowing in the pipe, say, imagine that the pipeline is transparent. That means the flow profile will be seen from outside. And see, the flow profile in the pipeline has been shown in the figure as first converging, then diverging. Like it looks like just like century map. So in that way, the flow profile looks. The flow profile would form in that. So here, there are two sections taken again. One in the bigger diameter, where the flow profile or flow is of by pipe diameter, and 2 again it is section 2 in the smaller diameter pipe, where the flow profile or flow is having smaller diameter, and there is a vena contract formation, smallest diameter of flow crystal formation somewhere in the sharp pipe, and it is named as CC. So, and accordingly, we name the cross sections also. A1, area of cross section of bigger pipe. A2, area of cross section of small pipe. CC, area of cross section of vena contract. So, I put here one question. What do you mean by vena contract? What do you mean by vena contract of formation? These are important terms. Almost 40 above people are there. Nobody is responding. I'm asking you a question. What do you mean by vena contract? See, unless the instruction a discussion time on or a two-way discussion, it would not help us either to you or to me. What do you mean by vena contract? See, for the sake of attendance, you, you are just joining the classes. Many faculty people observed, and it's not good. See, when a lecture is going on and it is uh, importantly meant for you, you should pay more attention, and you should pay uh, anything attention as well as should pay some heed to the subject. Okay, vena contracta ante enti? Why I'm answering, putting questions is because people are joining till the last minute. And of course, sometimes I admit and sometimes I ignore because of the lesson continuation, because of okay, let us see here what happened in sharp, sudden enlargement. Right? What happened? What has been shown in the figure? I explained the figure first. What has been shown in the figure? See, I repeat the two discussions: loss of it due to sudden enlargement, loss of it due to sudden contraction. These two discussions are very important. And these two, of course, derivations, which we can do, are very important for the examination point of view. Okay, vena contracta. This has been discussed in the venture also. ఏమైనా చెప్పరండి? Okay, uh, if you are inert, there is no use. You have to raise questions actually. When some lecture is going on, you have to interrupt by raising questions. And For the sake of latecomers or to admit them before the questions are answered, I will admit them. Only when these questions are answered. Just admitting joining to the class and ignoring. See, this requires just listening, nothing more than that. What has been shown in the figure? I repeat. See, because of importance of these two questions in the examination point of view, I'm concerned about your attention. బినా కాంట్రాక్ట్ అంటే ఏంటి? అసలు ఫిగర్ లో ఏం చూపించాము? వాట్ హ్యాస్ బీన్ షోన్ ఇన్ ద ఫిగర్? ఏమైనా చెప్పరేంటి? బినా కాంట్రాక్ట్ అంటే ఏంటి? ఓకే, specifically ask. Number 1 from B section. I don't know. You know or don't know? Number 1. So I have to assume that you are just joining and not listening. You are paying attention on other things. So Vina contracta is the మీరు చెప్పరా? Number 17, B section. Are you listening? Number 17. You tell me yes or don't know. Number 4 from B section. Number 7. Are you listening? Number 4 and 7. Number 67, A section. Are you there?
Sir. Yes, sir.
Then see, I'm putting a question. What do you mean Veena contractor?
Sir,
Veena contractor అంటే ఏంటి?
సార్ ఒకసారి మళ్ళీ చెప్పండి సార్, అసలు వినిపించట్లేదు సార్.
మరి చెప్పాలి కదా మీరు.
కాదు సార్, మీరు కాదు, మీరు ఇప్పుడే చెప్పింది వినిపించట్లేదు సార్. ఒకసారి మళ్ళీ రిపీట్
Veena
చేస్తారు క్వశ్చన్.
contractor. What do you mean by Veena contractor? Okay, Veena contractor is the smallest cross section of flow profile in this discussion, which was named as CC. CC, there you observe in the pipeline, there is smallest cross section of flow. That means the cross section, the flow is will form after diverging, it converges, and in between there will be formation of smallest diameter of flow. That smallest diameter of flow is named as Veena contractor, and it was discussed in the venturimeters also. And now, why I am much concerned about this point is because we apply Bernoulli's equation, we apply the equation, whatever equation between the Veena contractor and section 2. See, for example, from the Veena contractor to section 2, we can assume that it is enlargement of pipe, and we apply the equation, the earlier equation which was derived. So I'm admitting people, I don't know why they are joining. Okay, between section CC and section 2, it looks like sudden enlargement, and therefore we apply the equation for head loss to sudden enlargement. It is Vc minus V2 whole square by 2g. And now tell me which velocity is higher, Vc or V2? Just this is a common sense question. Which velocity would be higher, at CC or at 2? This requires the application of continuity equation. A1 V1 equal to or AC VC equal to A2. That application, you know, because A2 is a bigger diameter, has some bigger value than that at CC. Definitely, the velocity at CC would be higher. So in that way, you can tell. Now, Vc minus V2 whole square by 2g, we manipulate by mathematics. We keep V2 outside, V2 square by 2g. Just mathematical manipulation. And when V2 is kept outside, it will become V2 square. And now in the bracket will be Vc by V2 minus 1 whole square. And now, as I said, the continuity equation, AC Vc equal to V2. And why this continuity equation is because Vc by V2 has ratio of areas. See, AC by A2, which was discussed in the RFIS method. AC by A2, area at Veena contract of area at smallest cross section of pipe is called the coefficient of contract, which was discussed. So in that way, Vc by V2 is equal to V2 by AC. Vc by V2 is replaced by A2 by AC by continuity equation, and it will become 1 by Cc as from RFIS method definition, the definition of coefficient of contraction. from the orifice. And using this value, we can substitute in the equation for head loss between head loss between CC and 2, which is HEC contraction is equal to V2 square by 2 into 1 by CC minus 1 whole square. And the coefficient of contraction is generally varies from 0.6 or 0.6 to something. And we call CC is a constant, and 1 by CC minus 1 will be also a constant, and its square is also a constant. Therefore, we write SC value as K into V2 square by 2, where K is a constant, which is equal to 1 by CC minus 1 whole square. And this CC, if CC is assumed to be 0.62, then K is worked out to be 0.37. And however, the value of coefficient of contraction is taken in the problems, or it is recommended to be 0.5 into square by 2. And therefore, coefficient of contraction is 0.5 meter square by 2. Here, we have to raise some doubts. That slide I will share. So you see, though coefficient of contraction or head loss from CC to 2 is worked out to be 0.3 something meter square by 2g. And but the value of head loss to sudden contraction is taken to be 0.5 meter square by 2g. And like in the problems. So here you have to raise something. Why? So that why can be answered by looking into the flow profile, where there is sudden contraction, there is a convergent portion in the flow profile and a divergent portion in the flow profile. Maybe because we ignored the converging portion, that may be the reason why 0.5 meters per meter is considered head loss due to sudden contraction. Now here, see, the problems are shared because these are also very important, and these are very simple. First of all, not only important, these are very simple to solve. When a problem on head loss due to sudden contraction or sudden enlargement given. For example, if it is sudden enlargement, what we write V1 minus V2 whole square by G. That is velocity in short pipe V1 minus velocity in large pipe V2 whole square by 2. And if it is sudden contraction from section 1 to 2, then we will write head loss due to sudden contraction with HC equal to 0.5 V2 square by 2. The point of V2 in shuttle head loss with sudden contraction has to be remembered, which is higher velocity in a short pipe. That's why I asked in earlier case, what would be the velocity in the short pipe, and how you compare the velocities in short pipe and large pipe. Okay, you see the problem. Find the head loss when a pipe of diameter, some diameter is suddenly enlarged to a diameter, some double the diameter. Rate of flow of water through the pipe is given 250 liters per second. How do you convert 250 liters per second into meter cube per second? Okay, these are very simple questions. I don't know why you people are not answering. How do you convert? Why? Because if there is a problem of direct substitution by some people, but that is very dangerous. If you make direct substitution, erratic readings result, and it lead to 0 marks. And there is no doubt if this type of simple problems are given and if units are not followed, essay units are not followed, or appropriate units are not followed, definitely will not be given a single mark in the examinations, whoever is the examiner. And you see here, the problem is on sudden enlargement problem. And the sudden enlargement problem, here the pipe is 200 mm. That pipe diameter, short pipe diameter, is converted into 0.2 meter, and its area can be found. And it is enlarged to 400 mm, so A2 or D2. It is converted into meter, that is 0.4 meter, and area is calculated. And here the discharge 250 liters per second is converted into 250 into 10 power minus 3, and which is 0.25 meter cube per second. And the velocity is in the two sections, that is smallest section, that is 1 and large section 2 are V1 equal to 2 by A1, V2 equal to 2 by A. And in that way, the velocity is found. And then after finding V1 into head loss with sudden enlargement is found V1 minus V2 whole square by 2G. And in that way, we do the problem. And you see again, there is a sudden enlargement problem. At a sudden enlargement of water main from 240 to 480, the hydraulic grade here, this term can be explained in the later sections very clearly. But hydraulic gradient means it is the rise of hydraulic gradient, which is piezometric head difference, which is P1 by rho g plus Z1 and P2 by rho g plus Z2. The difference, whichever is higher, we write. For example, here P2 by rho g plus Z2 minus P1 by rho g plus Z1. It is given rises by hydraulic gradient rises. That's why the piezometric head at 0.1 is smaller and piezometric head at 0.2 is higher. Therefore, in that way, it rises. And it is therefore P2 by rho g plus Z2 minus P1 by rho g plus Z2. And it is given as 10 mm. And that it has to be converted into later. So 10 by 1000 or 10 into 10 power minus. So in that way, we write. And applying Bernoulli's equation between section 1 and section 2. As usual, here in the Bernoulli's equation, we do have the value, the difference between P2 by rho g plus Z2 minus P1 by rho g plus Z2 value directly. And because the pipe is enlargement loss added in the Bernoulli's equation in the right side. And therefore, here we write P1 by rho g plus V1 square by rho g plus Z1 is equal to P2 by rho g plus V2 square by rho g plus Z2 plus head loss to enlargement H. And that head loss to sudden enlargement is V1 minus V2 whole square by 2G. And this is substituted in the equation where here head loss to sudden enlargement is V1 minus V2 whole square by 2G. And in the substitution, we have to find out this velocity value first, velocity value, and then discharge. You are required to find the rate of flow. The discharge has to go. So from this equation, if you substitute HE, head loss fluid analogy, from the continued equation, A1 equal to A2. So there, A1, B1 is equal to something written, that is A2 B2 by A1, which is the diameters are given, and V2 in terms of V2, it is worked out. It is 4 times it is worked out. And in that way, in the sudden enlargement equation, HE, we substitute the value of V1, and it is worked out to be 9V2 square by 2G. And then there in that way, V1 is written as 4V2. And in the Bernoulli's equation, it is substituted as well as, and in the head loss fluid enlargement, it is substituted. And when we substituted in head loss fluid enlargement, we got some value in V2 square. And when we substituted in Bernoulli's equation, we write the value because P1 by rho g plus Z1, the difference between piezometric is given. Therefore, that is not required. Therefore, we replace P2 by rho g plus Z2 minus P1 by rho g plus Z2 is equal to 10 mm, which is 10 into 10 power minus. So that value we replace, and only we have V1 square by 2g and V2 square by 2g and head loss due to sudden enlargement. All these values are substituted in terms of V2. And when we substitute in terms of V2, V1 square by 2g becomes 4V2 whole square by 2g. And in the sudden enlargement place, we substitute the value which we worked out, 9V2 square by 2g. And the value of P2 by rho g plus Z1, Z2 minus P1 by rho g plus Z1 is replaced by 10 into 10 power minus. So replacing in this way, we get the equation, one equation in terms of V21, and that V2 is worked out, and then the discharge is worked out. And this is not the unique way of doing a problem. You can do the problem in any way. In terms of V1, you can calculate, you can substitute. In that way, you can try a procedure of your own choice. You can make it as a habit not to follow mathematical procedure in any textbook or any instructor. And instead, you follow your own procedure because mathematics is a flexible subject, and it has to be worked out by you, not by it has not to be by heart, nor it has not to be followed as it is given in the textbooks or as it is instructed by somebody else. So in that way, we do problems, and we have see this problem. There is this is also a model problem, and this type of problems are given in the examination. The rate of flow of water through a horizontal pipe is given. The diameter of the pipe, which is initially which is 200 mm, is suddenly enlarged to 400 mm. Here, the multiple questions are: the pressure intensity in the smaller pipe is given, 11.772 Newton per centimeter square. And we are required to find out loss of head due to sudden enlargement and pressure intensity in the large pipe and power loss due to sudden enlargement. And the power loss due to sudden enlargement is given by equation omega Q He by He, where omega is the specific weight of water and Q is the texture and He is the head loss due to sudden enlargement. And that, of course, based on the units, this equation changes based on the units we follow. And here, loss of head due to what is the loss of head due to sudden enlargement? What is the equation for loss of head due to sudden enlargement? Just okay. What is the loss of head due to sudden contraction? Loss of head due to sudden enlargement ఇప్పుడు discuss చేసాం కూడా. We substituted in a certain problem. See, if you listen to this type of mathematical lecture, definitely you will get good marks. And if you freshly go through a textbook, or if you freshly put your head in a textbook, it may be, of course, difficult for beginning. And if you listen to the lecture, if you read later, for example, it will definitely go smoothly, or more points will come into your mind than what you learned in the lecture. Okay, see, these three questions, that's why, because these are given, I told you this type of problems have been given in the examination. Because of a number of questions, sub questions in this problem, and of course they have different equations. And okay, what is the conjugate equation, at least? What is the continuity equation? Continuity equation ఏంటి చెప్పండి. Tell me the continuity equation. I'm asking. That's all. A1 equal to A2. With that continuity equation, we find, see, what is given, the rate of flow of water through the pipe is given, and diameter is given. So because the diameter is given, what is the first step to solve a problem? The numerical values have to be observed first. Then what next? what have to be converted. See, along with the numerical value, we have to write the units given in the problem. And if they are not in SI system of units, we have to change those units into SI system. That is the very important. Why we are at least to some possible extent we are instructing problems is because some fundamentals are there in solving certain problems, and those fundamentals are common to, of course, many problems. Now, the first step in solving a problem is to verify the units of the numerical values of a particular parameter. And here, here the discharge is given in meter cube per second, so it is SI system. Diameters in millimeter given, and they have to be converted into meter. And the pressure intensity at smaller pipe is given. So that is given in Newton per centimeter square, and it has to be converted into Newton per meter square. So in place of centimeter, you write 10 power minus 2 meter, and then its value will become some 11.77 into 10 power 4 Newton per meter square. So in that way, the units have to be converted. That is the very first step in solving the problem. And after that, see the writing the diameters in meters, the areas have to be found. Here, diameter D1 is written 0.2 meter, and its area can be found. Uh, See the area can be found, and then again area for bigger section that is zero point 0.4 meter. That is area is found, and then after finding areas, because discharge is given, what you can find from the discharge, if areas are known. See, both A1, E1 and A2, B2 are the equation for discharge. That means 2 equal to A1, E1 and also equal to A2. And discharge is given, and if areas are known, what will you know then? So if areas are known, the velocities can be known. The velocities can be known. For example, using 2 equal to A1, B1, you can find V1 equal to 2 by A1 and V2 equal to 2 by A1. In that way, the velocities can be found. And the very first question in this problem is to find loss of head due to sudden enlargement. And that HE, I asked you, what is the head loss due to sudden enlargement? What is the equation for head loss due to sudden enlargement? See, unless you practice while the instruction is going on, or while the person interrupts by putting the questions, then you have to at least look at the equation. The head loss due to sudden enlargement is, what is head loss due to sudden enlargement? And this head loss due to sudden enlargement is written as HE. H subscript E. And that is B1 minus B2 whole square by 2G. So this has been derived in the last class, and this has been discussed in the last class. Because V1 and V2 are known, we can find by substituting. And see, once A1 and A2 are worked out in meter square, and because 2 is given in meter cube per second, if not given, you have to convert it to meter cube per second. Then velocities V1, V2 would be worked out in meter per second. And the value of G you substitute 9.81 meter per second square. And in that way, you will find He value in meter of head, meter of water, meter of the liquid fluid, whatever it is. And here it is worked out to be some 1.816 meter. So that much. What do you mean by head loss actually? Physically, I told you how do you visualize head loss in some enlargement or a contraction, whatever. How can you visualize? This has to be understood very clearly. How can you physically visualize? See, I told you that at two sections, if you put piezometers are nothing but vertical glass tubes. If you put two piezometers at section 1 and 2, there will be a drop in the liquid level in piezometers. First, the liquid level rises into the vertical piezometers, vertical glass tubes, which you put at section 1 and the section 2. They rises. And if you observe after the rise is stabilized after steady conditions, what will you observe? The height of the liquid level in the some certain section 2 would be a little bit lesser. And that is what head loss due to enlargement or contraction. That is how head loss due to some head loss is observed. So in that way, you have to visualize. Don't head loss. What is head loss? That has to be understood. That means the the pressure at section 1, and when pressure at section 2, the pressure at section 2 will drop. That's why in the second bit, you are asked to find the pressure also, the pressure, because it would not be same. It would not be same because there is head loss. And if it is a uniform pipe, and because if you take V1, V111 and 2 at any two sections in uniform diameter pipeline, then V1 equal to V2, Z1 equal to, and there would not be any head loss, and there would not be any rise of any fall of liquid level in piezometers, and then P1 equal to ultimately. And here, because there is sudden contraction or sudden enlargement, and because therefore there will be head loss, definitely pressure at section 2 will be different, and therefore you are required to find out that pressure. And writing the energy equation or Bernoulli's equation, we write the Bernoulli's equation, and you substitute in the value of P1, the value of P1, and the head loss to sudden enlargement, it is worked out, and the value of P2 is not that P2 can be worked out. It is worked out to be 12.96. Of course, it is, of course, I don't know why in the textbook it is worked out all the times, many times in Newton per centimeter square, but it is not suggestible to you. I suggest you to follow SI system rules. Always use Newton per meter square. And power loss due to sudden enlargement, I told in the beginning, P equal to omega, and which is omega is specified density into discharge. That density of water is 1000 and discharge it is given in the problem itself. It is 0.25 meter cube per second and G into He. And because see 1000, I told you, depending on the units required, we substitute the equation. Here, unnecessarily he divided by 1000 and work out in kilowatt. But no necessity. We can use simple formula P equal to omega H, and that can be worked out in watts. Okay, we will stop here.